People have also been looking at more complicated convolution filters, and for theoretical reasons. An example are these Gabel filters. The Gabel filter is a Gaussian, as you can see here, but modulated with this cosine function. So rather than having a Gaussian, you will have it with ripples coming from that cosine. Of course, that cosine has a certain frequency, a certain orientation. This is a spatial domain. And you see we have a product. We have a Gaussian, we have a cosine. As we have seen from the properties of the Fourier transform, this means that in the Fourier domain, this filter looks like a sum of two Gaussian filters, because here we have a product of a Gaussian and a cosine. The Fourier of a Gaussian is a Gaussian, but if you widen that, the Gaussian in the Fourier space will sharpen, and vice versa. And the cosine, you think the cosine only one frequency, you get these two peaks, these two Dirac impulses around u and v0. Now, this is also multiplication. The convolution theorem tells it becomes a convolution. So now we have the convolution of the Gaussian in the Fourier space with the pair of Dirac impulses there. And that convolution of a Gaussian with these two Dirac impulses amounts to copying the same Gaussian but around each of the two Dirac impulses. So here the Gaussian was still around 0, 0. Here it will be centered around the position of these two peaks in the Fourier domain. So you have these two copies of these two Gaussians. That's a result of this convolution. Don't have to care too much about the details of the mathematical expressions here. Here we see it, but all graphical. So the spatial domain gives us this kind of thing. You see here this kind of Gaussian envelope, but then modulated with this cosine. And this is a Fourier part of the same story, same filter. You have these two copies of the Gaussian around the two Dirac impulses. So u0, v0, 0 is in the middle, and we have now the Gaussian placed around that frequency on both sides, mirrored. Correspond to the two peaks that are coming from the cosine in the Fourier space. And that makes this Gabel filter again interesting because it localizes, right? So you have a certain area where you can say there are substantive values for this spatial domain filter, and out of which it gets pretty much 0. So it's localized at a certain place in the image, like of course loss filters also have. They're also bounded in space. But then in the frequency domain you get this kind of behavior. You see that actually what this filter does, it is selecting certain frequencies in the Fourier domain. It's like looking at the presence of certain frequencies in the Fourier domain of our texture, and it's not very much interested in all the rest. So it's also very well localized in the frequency domain. Now, why the Gabel? Because you can say, yeah, but this is also not so different from what we have in loss filters, right? Well, there's a unique theoretical optimality here, and that it says that the variance of these two filters combined, the product, reaches the absolute minimum, theoretically minimum value. So that means a Gabel filter is the kind of filter that has the best combined localization in both the spatial domain and the frequency domain, and that's a theoretical reason to use this filter. Now, of course, in practice you can't implement it ideally and so on. So, personally, I believe that the reason to use this filter, this more complicated filter, is maybe a little bit overstated, overrated. Yeah, it's a theoretical justification. You can't forget about that. It's specifying the variance in the spatial domain and the frequency domain of that filter. But the important thing is here, combining these two variances, if you take the product, you have the theoretical lower bound here. You're always above that. But for a Gabor filter, you reach equality. You are at a very minimum value. It has the best combined localization in the spatial domain and the spatial frequency domain together of all possible filters. So it's kind of Heisenberg, a certain principle here. You can't have perfect localization in both. But anyway, we reach the equality. We are not strictly larger than for the Gabor filter. Okay, of course, we said we will have these filter banks. We also will have different Gabor filters, so we will combine multiple Gabor filters. It's not just a single one. Here we are looking at the spatial frequency domain, and we see where these two peaks, these two Gaussian peaks are positioned. We only show one of the two Gaussians. So that will be the center, U and V0, and then see we put different Gaussians at different locations. And of course in the spatial domain we have the corresponding Gabor filters corresponding to these Gaussians in the spatial frequency domain here. And what you see, and that's why we choose in this case the Fourier domain to discuss, that we try to kind of sample this entire space. Right? You see in different orientations, you have different of these filters. They correspond to the same orientation of the cosine with different frequencies, lower frequencies and higher frequencies. And you do that in different directions. So we are in fact back in this exercise of sampling in fact different parts of the spatial Fourier space so that we can say things about directionality, periodicity, coarseness, and so on. And that gives us again a feature vector. So we apply all these filters everywhere in the image. So this entire set of filters we apply to every location in the image. We take the output, we probably square it and average again in a small environment about the pixel, and that gives us a feature vector that we then pass on to the classifier. An example, so we have this texture on the left, and this is one kind of Gabor filter, and that would be another. So here you see these cosines were oriented horizontally, and here the cosines were more oriented vertically, right? And these two different Gabor filters bring out different aspects of this texture. Because we have these different orientations, different frequencies, and so on. So, we are well versed to characterize the texture. Okay, so far we saw loss filters and Gabor filters. And in both cases, the filters were fixed, predefined. Now we will see eigenfilters. And that is different, because now we will adapt the filters, convolution filters, to the texture, and also possibly to the imperfection that we want to detect in some inspection task. But mainly to the okay texture. By the way, this technique of eigenfilters was first introduced by Frank Ade here at ETH. Okay, so filters adapted to the texture, that's the main difference here. So that also means we will have to extract some information about the texture before we can actually derive our filters. So here's the idea. We have a mask and we shift it over several training images. And typically the training images will have good quality texture. So if you are, for instance, involved in some textile inspection, these images will have good textile in them. And we shift a mask across the entire image. And then we see the different pixels in that convolution mask. They are at each position covering a certain pixel. what are the intensity statistics for these different pixels. And what we actually want to do is to apply principal component analysis. So we want to extract eigenvectors from that information and then based on that define eigenfilters. What PCA will do, of course, is it will give us a new representation of the original information, but now rank ordered according to variance. So our first convolution filter will be the filter that corresponds to the largest swing in its outputs, the largest variance if we apply it to the image. And the last convolution filter will probably almost like have a constant as its output. And then we will apply the different filters corresponding to the different eigenvectors to the entire image and use that as a filter bank as before. Now this may all still sound very sketchy and mysterious. Let's try to explain a little bit further what we mean here. Here's an example. It's a denim, so it's a textile. And what we want to do is to detect certain flaws. I hope you can see this. So in the red rectangle here, you see that here this erroneous part is faulty. In fact, there is a thread missing that had to go through horizontally. So the weaving machine, the loom, missed out here with one thread. It's missing. And it's a quite visible defect. So you want to inspect that while still weaving. You don't want to weave a lot more material with this kind of mistake happening again and again. Maybe it's something wrong with the machine, maybe you have to do some adaptation. So it's often important to detect errors as soon as they occur, still on the weaving machine, on loom detection. Okay. So the best way probably to see a deviation in a pattern like this is to look at what is the typical pattern and then to detect the outliers, the deviations from what is typical. So what's typical here is also that you have a period, kind of a periodic intensity pattern. So you want to see at which places that kind of period does not really appear, there's a deviation from it. That's probably a good way of looking at those mistakes. And that's also what we will going to do here. And notice that these eigenfilters are indeed best for these kind of periodic problems where you have very typical patterns, the deviations from which you want to measure. Now, the problem is if you want to specify what is typical, how a typical period of a pattern like this looks like, these periods are pretty big. Now, we have to zoom in quite a bit onto the textile to detect even small errors. But that then also means that a period becomes pretty big. In this case, this particular inspection system on that loom, there were 17 pixels horizontally and 13 pixels vertically. That's a single period. So that kind of intensity pattern within that 17 by 13 area will repeat itself more or less if you put one period next to the other. Now, if you have a 17 by 13 convolution filter, that's a huge convolution filter, even for modern hardware. So you don't necessarily want to drag that around. And also note that this is then not a single filter, there will be multiple filters of that dimensionality. So we want to have a more parsimonious approach. And the way we do this is by only reading out information at a few selected positions. And that turns out to be very effective. So what we do is, rather than being interested in information 17 by 13 pixels and generating a convolution filter for the same dimensions, we only look at the green places here, the green positions in this convolution filter. So the red thing still is one period, but we will only look at these 9 different intensities. So what we will do now is we will take that sparse filter, only look at the green positions, shift that 17 by 13 filter over the entire image, reading out these 9 values at every position of the filter, and just get the statistics for those 9, including the covariance. So that's important. Because otherwise, of course, it will be pretty much the same statistics, same distribution of intensities. But you also look at how the relation between the different intensities is. So you also look at the covariances of the different intensities among these 9. And that tells you a lot about the pattern that is typical for the textile. Here's the resulting covariance matrix for that denim picture that we saw before. So that's the covariance matrix, as we know for PCA. Now, if you want to know the eigenfilters, we have to look at that covariance matrix and look for the eigenvectors of that covariance matrix. So we look at the, in this case, 9 eigenvectors of this covariance matrix, and then we fill the green spots that we had before with these values, every eigenvector yielding 1 convolution filter. So one eigenvector will have 9 elements. These are used to fill the 9 different green spots that we had before, and that gives us 1 convolution filter. We do that for each of the eigenvectors, thus getting 9 convolution filters in the end. Here are the eigenvectors from largest variance to lowest variance. So I want now to exemplify the construction of one of these covariance filters from those eigenvectors. So the generation of an eigenfilter from an eigenvector here. And we will look at this first eigenvector, the eigenvector coming with the highest variance, its output. So if we multiply on that direction, we will have the highest variance. That translates into, if we convolve the image with the corresponding eigenfilter, we will have the largest swing in its output value. Okay, we look at that top left eigenvector here. Here it is. So that's the filter with the highest variance, as I said. We will see that this filter captures the underlying intensity pattern very well. And basically this vector indeed reflects this pattern. So if you look at it, this is like plus 1/3, minus 1/3, plus 1/3, minus 1/3, plus 1/3, minus 1/3, plus 1/3, minus 1/3, plus 1/3. Okay? Not quite, you see there are a little bit of variations around these values, but basically that is what this filter is like. And here is how we've built this eigenfilter from the eigenvector. You see that different components of the eigenvector are filled in at these 9 spots of interest in the sparse eigenfilter. And so we have 1 convolution filter as a result of this 1 eigenvector. And for each eigenvector we get another convolution filter through that mechanism. And indeed, as we said, this is the first eigenvector, so if we move that filter with these values over the entire image, the output has the biggest swings. It captures the underlying periodicity very well. Namely, this kind of pattern, if you look in detail at this textile, it's kind of this pattern that you get. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, bright spot. And you can imagine that if you shift a filter like that around over this image, at one position, all these green spots will lie at the very minima and maxima of intensity, like here, here, here. The green positions there, they are on the maxima and the minima of intensity. But if you shift them by half a period, this point will come here, the point that was here comes here, and you have a reversal. Now it's exactly the opposite. Where you were at the maximum, now that pixel, that position in the convolution filter is at the minimum. And if you were at the minimum before, now you're at the maximum. It gives you the biggest change in outcome, because you have all these signs also going on, minus and plus. So you have the biggest swing in the output. So convolving the image with this filter gives the biggest swings variance as the position and as the positive and negative values go from an intensity top, like here, to an intensity value, like here. And here we have the result on our example image that we saw before, with the flawed denim. Here the 9 filters have been applied to that image. And in fact they have been also a bit justified to see some changes in the output. That maybe should not have done that. Because here you have a far higher variance than for the lower one, low variance one. If we then don't only look at the local value of the convolution, but take the square and average in a small region, as I announced one typically does, for these filter banks before using a classifier, you start to get something like this. In what you probably heard about PCA so far, the typical explanation is, oh, the eigenvectors with the high eigenvalue, those are the important ones, because they will pull apart the instances of different classes and will therefore simplify your classification problem. Whereas if you have an eigenvector with very low variance, that will jumble all the information together. You won't see the difference between different classes anymore. So use the ones with the high eigenvector, the high variance. That is no longer true here. And one of the reasons is that, of course, this whole thing is trained on correct dimming. It's not trained on any flaw. And you never know how a flaw will manifest itself. True, probably the chances are a bit better if you have a small variance to fall outside. So if you have a big variance on correct dimming, the high variance filters here, the chance, if you apply the same convolution filter to a flawed area, to fall inside is pretty big. But if the correct dimming gives you a very small interval, the chance of falling within that interval again, but now with a flaw, at a position of a flaw, is pretty small. And that already indicates that this law of used for the high variance filters is not so true here. Okay, this is inspection. So it's often advantageous to have a small interval of correct values for the correct textile, so that there is a higher chance of falling outside once you are at a mistake, at a flaw. And you see that happen here. You see that these first filters don't show so much change in this energy outcome, but it's mainly here these filters with smaller eigen values, with less variance, where the distinction between the flaw, this missing thread here, and the background is bigger. Here it's very good, here it's also very visible. And these are not the top variance filters. That's important to realize. Okay. So you can then combine these different filters in the end in one expression. We won't go into that. It's based on the Mahalanobis distance. It's a well-known statistical concept. Doesn't matter too much what it is. That's the result. And in fact, difference between floor and background, correct background, is so strong that in this case you can threshold to find the floor. You will find this area indeed. Okay, so here other example. This is more like a rule structure kind of thing. So here the texture is coarser, so the period will indeed be larger even than in the previous case. That's kind of a period, 47 rows, 21 columns. You can start to begin convolving an image with that kind of gigantic convolution filter, because also the images used here are, of course, very large. So we use the same trick. We use a sparse filter instead. We use these corners and then the midpoints, the same kind of 9 positions that we used before. Then we shift this structure over the image and we look at the covariance matrix for the underlying intensities. And this is the result. For that matrix, as before, we will extract the eigenvectors. We apply PCA again. And here are the different eigenvectors, the columns. And that's the variance. You see far more variance in this first one than in the last one. And by the way, same kind of story here. If you look at this first one, it's the one that typically captures the idea of maximum intensity, minimum, maximum. These are more or less the same values, but with plus or minus signs, if you look at it carefully. So it's a very similar kind of basic pattern that comes out. But as before, it's not necessarily the vector with the larger variance that will be best. To the contrary, you have reasons to expect maybe to be more successful with those eigenvectors that have a smaller variance on the right hand side here. Here's an example with a floor. You have this kind of greasy pattern. This is probably a wheel turning over the textile, leaving behind this kind of oily trail. And of course, again, you want to stop as soon as possible, right? Once you have an error like that, you don't want to weave 5 more kilometers of that kind of textile that you can then basically throw away. So you want to detect, and therefore you want, as soon as possible, so you want to detect en loon. Okay. Same story, we have our eigenfilters. So here's the one with the biggest swing. You see there, quite a bit there. So it's difficult to predict in this case where the flow will show up, for which filter it will be. It's also not necessarily always a filter with a smaller eigenvalue, with the smaller variance. That's also not a conclusion you can draw. But often these are the better filters for the reasons I mentioned. But not necessarily, not always. So here are already 4 filters, again of the 9 in total that we have. With left hand side the outcomers filter and here the energies. So calculated as the average of the square around the pixel. That's the energy. And that's the thing we typically use for the final decisions. Notice that in this case, for instance, this filter is particularly good. It's number 6 in the row of 9. Again, same story, we can combine the output of all the filters at no resistance and then simply threshold this one and we will find that flaw. So, and as we have seen here, that's the important thing. In this case, the filters were really engineered to go with the textile, with the texture in question. And that's the difference between this eigenfilter approach and the Loss and Gabel filter approaches that we saw before. Thank you for your attention.